Hi, I'm John Ting. I'm a first-year PhD in Dr. Incorvia's lab, and today I'll be talking about multiferroics. So multiferroic materials exhibit more than one of the following properties: ferromagnetism, ferroelectricity, ferrotoridicity, and ferroelasticity. But for reasons that I'll explain later, researchers are primarily interested in the combination of ferroelectricity and ferromagnetism. So we all know what ferromagnetism is, so I'll go a little more in depth on ferroelectricity. So a ferroelectric material has a spontaneous electric polarization or spontaneous net electric dipole moment. So you can think of it as the electric analog of ferromagnets. And the electric polarization arises when the symmetry in the crystal structure is broken. For example, here we have a perovskite ferroelectric. And using an electric field or strain, you can move the location of the titanium 4+ ion relative to the crystal structure. And when you do that, you're essentially redistributing the charge and creating an electric polarization. And ferroelectrics are useful because you can use them to store information like with magnetic memory. So in multiferroic materials, these different phenomena like magnetism and ferroelectricity couple to create interesting effects. And two of these effects are the direct and converse magnetoelectric effects. The direct effect describes how a magnetic field can control the electric polarization of material, whereas the converse effect describes how an electric field can control the magnetization. And there are basically two major types of multiferroic materials, single phase and composite. A single phase material is basically a single material in which the electric or magnetic field directly induces a change in the magnetization or electric polarization. But a composite material is composed of discrete parts. For example, you can have a magnet on top of a ferroelectric layer. And the mechanism is essentially the same, except it first induces a strain, which then changes the magnetization or electric polarization. So in order to understand how to create a multiferroic material, you have to understand where ferroelectricity and magnetism come from in the first place. So you can think of it as a path. So for ferroelectricity, there are two paths to attain that in a material. The first one is d-zeroness. And what this means is that in materials with an empty valence d shell, the energy barrier needed to break the symmetry tends to be decreased. So many of these materials tend to be ferroelectric. And the second path is lone pair stereochemical activity. And what this means is that if a material only has exactly two valence electrons, these electrons tend to orient themselves in such a manner to create a net electric dipole moment. And similarly, there are also two paths to magnetism, which we know about, unpaired d electrons. And for rare earth metals, unpaired f electrons also lead to magnetism. So essentially, if you take one path to ferroelectricity and one path to magnetism and combine them in a single material, you can end up with a multiferroic material. For example, bismuth iron oxide is multiferroic. And the ferroelectricity comes from the 6s2 electrons on the bismuth 3+ ion, whereas magnetism comes from the 3d electrons on the iron atom. And recently there was another material called europium titanium oxide, which was discovered. And the ferroelectricity and magnetism come from slightly different origins. The titanium 4+ ion has no d electrons, which provides the ferroelectricity. And the magnetism comes from the europium 2+ ion, which has unpaired f electrons. And that's a bit of an unconventional mechanism to attain magnetism. So yeah. And so back to the first slide, and why are we so interested in multiferroic materials? And the main reason is because in multiferroic materials, you can use electric fields to control the magnetization. And this tends to be a lot more effective than spin transfer torque, which we learned about. So STT is currently the dominant way to control the magnetism in a material. But there's an inherent limitation because the magnetic moment of a single electron is equal to one Bohr magneton. And because of that, one electron is only capable of changing the orientation of one Bohr magneton. And as such, the current increases linearly with the magnetic moment. So if you have like a large array of memory cells, you need quite a high current to switch them. So for a typical STD device, around 10 to 11 amps per meter squared is needed. And this consumes around 10 femtojoules per device. But using electric fields, a typical electric field control device consumes only around like 10 attajoules, which is like 3 orders of magnitude lower than for STT. And this is the main driving force behind the research effort in multiferroics. And to understand how electric fields can control the magnetism, you really have to look at the total energy of a multiferroic system. So we have this pretty complicated equation, which shows that the energy comes from exchange interactions, magnetocrystalline anisotropy, elastic energy, surface anisotropy, exchange anisotropy, and stray fields and external fields. So by manipulating these different terms, you can induce the magnetization to change. So, so one of the mechanisms that has been discovered recently has to do with the third term, which describes elastic energy. So if you look at the third term, epsilon represents the total strain of the system, and epsilon naught represents the eigenstrain, which basically describes like the strain caused by like the magnetic moments. So if you apply an electric field to a multiferroic material, due to the fact that ferroelectrics are inherently piezoelectric, this induces a strain in the ferroelectric material. And this strain ends up then exerting a strain on the, this causes epsilon to increase, which increases the total energy. And in order to decrease the total energy, the magnetic moments have to rotate to reduce the total energy. And when they rotate, they cause the eigenstrain term to increase, which ends up decreasing the total energy. And this is one of the mechanisms that can be used in magnetic memory. So on the left, we have a typical magnetic tunnel junction. So we all know how that works. But one of the major problems with magnetic tunnel junctions is that the dielectric layer, like the blue layer in the middle, is an insulator. So when you run large currents through it, it tends to degrade over time, which reduces the durability of this device. But if you insert a ferroelectric layer below the magnetic tunnel junction, the coupling between the ferroelectric and the free layer on the bottom allows you to control the magnetic moments of the free layer using an electric field. So if you look at the figure on the right, you can control the free layer magnetization by applying an electric field between BL2 and PL. And if you do it this way, there's essentially no current that flows through the device. But you still need to use a current to read the state of the MPJ. But read currents tend to be a lot lower than write currents. So the device on the right is essentially an infinitely durable device. So researchers were able to get a density of 88 gigabits per inch squared with this type of device, compared to industry, which is around like 1 terabit per inch squared. It's not quite there, but due to the increased endurance and energy consumption, it is quite promising. So here's a table comparing, so the device I just described is SME RAM, which is on the far right. And you can see that the storage capacity, write and read time are quite comparable to like STT, MRAM, and other leading technologies, but the write energy tends to be significantly lower. So yeah, this is a very promising direction in the field of memory technologies. That's it.